Assalamu alaikum students. In our last lecture, we discussed about the one-dimensional Ising model. So today we are going to discuss few problems related to this model. So consider the first problem. Consider three Ising spins at the vertices of a triangle which interact with each other with a ferromagnetic Ising interaction of strength J. Make a correction. This is interaction. So find the partition function of a system at temperature. So here, the problem is that you have three spins S1 and S2 and S3 which are present at the vertices of a triangle, and you are asked to find the partition function for such a system based on the Ising model. So as we know that in order to find the partition function, what we need is we need to find out the energy eigenvalues of the system. And for according to Ising model, the Hamiltonian of a system is given by H is equals to minus j summation of ij to n si sj minus mu b summation of I si. So as we discussed in our previous lecture, that this first term is the Heisenberg exchange interaction, which is the interaction between the nearest neighbors only, and the second term is present whenever there is an applied magnetic field. So as in the question there is no applied magnetic field, so this term will be equal to 0. So we will be left with H is equals to minus j summation of ij, si and sj. So here we are considering three spins S1 and S2 and S3. And in this model, we have to consider only the nearest neighbor interaction. So we will consider the interaction between S1 and S2, S2 and S3, and S3 and S1. But one thing that we need to make sure is that we have to count this interaction only once. So it means that this S1 will interact with S2, S2 will interact with S3, and S3 will interact with S1. Means that this summation will have three terms. So H is equal to minus J S1 and S2, the interaction between S1 and S2. And similarly, you will have the second term S2, S3 plus S3 and S1. And we know that the S1 and S2 can only take values plus minus 1, and if the spin is up, the value will be plus 1, and if the spin is down, the value will be uh, minus 1. That is, if this spin is upward direction and this spin is also upward direction, so we will have plus 1 for this side and plus 1 for this side. So this product S1 and S2 will give you 1. And similarly we can solve other products based on the arrangement of spins on two different sides. So keeping in view the arrangement of spins on different sides, we can make eight different possible combinations of these three spins on these three lattice sides. So the first possible arrangement is that all the spins are in the same direction. That is, all three spins are in upward direction. So the energy eigenvalue, which is equal to minus j s1 s2 plus s2 s3 plus s3 s1, will give you minus j into 1 dot 1 because the spin is up. So we will take a value of plus 1. So 1 dot 1 here and 1 dot 1 here. So the energy eigenvalue for this arrangement will be equal to minus 3j. Similarly, the second possibility that we may have is that the first spin is up, the second spin is up, and the third spin is down. And or we may have the possible arrangements that the first spin is up, the second is down, the third one is up, first is down, second is up, third one is up. So we may have different possible arrangements of spins in this case. So if we calculate the energy eigenvalues for all these three systems, we will see that energy will be equals to uh, plus j in this case. So similarly, the other possible combinations that we may have is that we may have all three spins pointing downward, or we may have two spins pointing downward, one upward. So there are total eight possible microstates for this system. And if we recall, we can calculate the number of microstates easily by simply doing these techniques. That is, the two represents the possible variations in spin. So in this case, we can have two states of spin. That is, it can either point upward or either it can point up downward. So there are three spins. So 2 power 3, we have total of eight microstates. And you can similarly you can calculate the energy eigenvalues corresponding to each microstate, and you will see that the microstates which have an energy is equal to minus 3j. The degeneracy for this energy is 2. That is, we have two microstates corresponding to the energy minus 3j, and this is the microstates when all the three spins are in upward direction, or all the three spins are in the downward direction. So the other possible energy eigenvalue is equals to plus j, and there are six such cases. So the degeneracy for this energy eigenvalue is 6. So we are going to find now, once we have find out the energy eigenvalues, we are in position to find out the partition function, which is the sum over all possible microstates of the system. So in this case, z will be equal to g1 exponential of minus beta e1 plus g2 exponential of minus beta e2, where beta is equal to 1 over kbt. So putting the value of g1 and e1 and e2, we will have z is equals to 2 exponential of 3 beta j plus 6 exponential of minus beta j. So this is the required expression of the partition function for the case of three spins which are arranged at the vertices of a triangle. So let's discuss another problem. And the statement of the problem is that consider a system of two Ising spins S1 and S2 taking value of plus minus 1 with interaction energy given by E is equal to minus J S1 and S2. So when it is in thermal equilibrium at temperature T, for large temperature, the average energy of the system varies as C over kBT. So what is the value of C? So what we are going given in this question here, that we are given two spins. So we are asked to find out the average energy for this system, which is in thermal equilibrium at temperature T. And then from that expression, we will find the value of this constant C. So let's move forward. Since in this case there are only two spins which are present and there is no applied magnetic field, so the Hamiltonian will have a term of will only have the first term, that is the Heisenberg exchange interaction is equal to minus j summation of ij, si and sj. So you will have exponential of minus j s1 and s2. That is uh, uh, you will have the interaction between only these two spins. So now the possible energy levels of the system are as follows. There can be four different possible combinations, since you may have both spins up, or you can have both spins down. But you may have two other cases as well, that this spin can either point upward, or this spin can either point downward, or this spin can point downward, or this spin can point upward. So there are four possible microstates of the system. So when both the spin point upward, the energy is equal to minus j, and similarly the energy will be minus j when both the spins are in downward direction. Whereas for the other two cases where one spin is up, the other spin is down, the energy eigenvalue is equals to plus j, and the degeneracy for both these cases will be equal to 2. So simply we can find out the partition function for this system, which will be equal to 2 exponential of j over kbt plus 2 exponential of minus j over kbt, which will be equal to 4 cos hyperbolic of beta j. So here you are asked to find out the average energy of the system, and we know that the average energy of the system is given by summation of GI into Pi, which is equals to exponential of minus EI over kBT divided by Z. So opening the summation, you will have a GI EI G1 E1 exponential of minus E1 over kBT plus G2 E2 exponential of minus E2 over kBT divided by z. We already have found the value of z, so just plugging the value of z here and putting the values of e1 and e2, you will get this expression, which can be simplified, and you will see that the average energy of the system will be equal to minus j exponential of beta j minus exponential minus beta j divided by exponential of beta j plus exponential of minus beta j. Since we are asked, given that we are only uh, find out the case when the temperature is very high. So for large T, we know that J over KBT will be less than 1. So if this is the case, we can open this exponential, which is equal to this uh, sum. And we know that in this case, we will keep only the first two terms, since the temperature is very high, so we can neglect the higher powers. So exponential of j over kbt will be equal to 1 plus j over kbt. So plug in this value in above expression, you will have this term, and after simplifying this expression, the average energy of the system will be equal to minus j square over kbt. So as it was given in the question that the average energy of the system varies as c over kbt, so it means that we can compare this expression with our final result. So c over kbt is equal to minus j square over kbt square. So from this equality, we can note that the c is equals to minus j square. So this is the required answer. So that's it for today's lecture. So you can see that these are very simple problems which belongs to the Ising model. Thank you.